for the power electronic converters, in order to obtain its body plot, we first need to calculate its transfer function. So in this section, we are going to use buck boost as a case study to learn how to derive its transfer function. So first, let's plot the small signal model for the buck boost topology. Actually, previously we used the basic averaging method to derive the small signal model. So here I just plot the small signal model of the buck boost converter. So here is the AC input source. And on the input side, we have a current source which reflects to the controlling part. I is the DC current for the inductor. And we have a equivalent transformer here whose turns ratio equals to 1 to D. So this is a AC transformer, not a real transformer. So we use this wave line to indicate that this is a virtual transformer. And in the middle stage, we have the inductor behavior L. And also we have a independent source, which refer to the controlling part as DC input voltage minus output voltage times small signal D. And this goes to the second transformer. For this second transformer, the coupling points are inverted. And also, we mark that it is a AC transformer. On the secondary side of the second transformer, we have the independent current source, which refer to the controlling signal. This term is ID cap. And the turns ratio for the second transformer equals to D prime to 1. And we have a capacitor in the output stage and also the load resistor, R. So here is the output small signal voltage. So for this typical basic averaged model for buck boost topology, we have the external controlling signal, which is the D cap, right? Control signal as control input. So we usually denote those quantities in S domain for our convenience to derive the S domain transfer function. So based on this small signal AC model, we can calculate the expression for the output signal. Basically, the output signal is determined by line input and also the controlling input. So we can write the expression for output signal in S domain into two parts. First part is controlling signal part. So its coefficient, we denote this as the GVD, which is the control to output transfer function. And the second part will be the input voltage part. So its coefficient is the line to output transfer function. So basically, we can see that we have two transfer functions in this output voltage expression. So we can analyze them one by one. First, let's look at the GVGS. So as I just mentioned earlier, we call this as the line to output transfer function. line to output transfer function means that this reflects how the input affects the output voltage. So based on the full expression, we can see that in order to calculate GVG, we just need to set D small signal to be 0. So we can obtain the definition for GVG. It's defined as the output signal divided by the related input signal. Under the condition that the other input is set to 0. So based on this assumption, if D cap small signal equals to 0, regarding this small signal model, right? So this current source, if the current is 0, means that it's equivalent to open circuit. And for the voltage source, if the voltage is 0, it can be replaced by short circuit so that we can plot the equivalent circuit under this assumption, right? So it is with this current source will also be 0, right? 0 will be open circuit. So here we can get the resulting AC equivalent circuit model. So the first transformer still exists as 1 to D, inductor here, and second transformer. D prime to 1. So here is the coupling point as identical, but second transformer coupling point are inverted. So we still use that, a waveline to indicate this is a virtual AC transformer. And on the secondary side, for the secondary transformer, we only have the C and R left. So this is the output voltage in S domain. So based on the resulting equivalent circuit, which is much simplified because we set DS to be 0, so we can do further manipulation to this circuit to calculate the GVGS. So the first step, we can push the input source and the inductor here, which is L, across the two transformers to the secondary side of the second transformer, right? We can get the resulting equivalent circuit. So basically the voltage source, if we push it, right, push VG S and L through two transformers, the voltage source will be pushed through two transformers. So the resulting value here will be minus, because this is opposite, right? Minus D prime over D will be D over D prime VG small signal. And inductor will be pushed through the second transformer. So the resulting inductance will be equal to L over D prime square. C and R are the same, unchanged. And here is the output signal. So if we look at the simplified equivalent circuit, we can see that this is essentially a impedance voltage divider, right? So it's easy to calculate the ratio between the output voltage and the input voltage, which can give us the GVG, right? GVG. So basically, GVG in S domain equals to output voltage divided by input voltage based on the voltage divider principle, right? This will be equals to two parts. First part is this one, minus d over d prime, multiplied by the voltage division ratio for this impedance network. So the numerator will be impedance of the C parallel with R. In S domain will be R parallel with 1 over SC. And the denominator will be the sum of impedance of L and C parallel with R. So for L is SL over d prime square plus R parallel with C. So we can go further to simplify this expression. We have a principle to calculate the parallel of two impedances. So the result is that GVG equals 2 minus d over d prime times the numerator is R and the denominator is R plus SL over d prime square plus S square RLC divided by d prime square. See, this is a quadratical expression in the denominator. So we have just learned the quadratic pole response. So we can normalize this expression. So we can normalize this transfer function to the standard format. So GVGS will be equals to the product of a DC bias, which we denote as GG0, times the quadratic pole response, which is 1 divided by 1 plus S over Q omega 0 plus S over omega 0 square. Then we compare those two standard format and original format. We can match those coefficients to see what is their expressions. So first we care about is this one. So we call this as GG0. We usually refer this to DC gain. So GG0 will be equals to this term, right? Because here R is canceled here and here, so 1 will be in the numerator. So DC bias will be equals to negative d over d prime. And second one is we care about is the omega 0, which is the frequency of the quadratic pole, right? Frequency of the quadratic pole. So we compare this atom with this atom. We can write the expression for omega 0 equals to d prime over LC square root. And the third one is Q. Q is the quality factor, right? So we compare this one and this one, so we can solve the expression for Q. Will equals to d prime square R over L times square root LC divided by d prime. So d prime can cancel with this d prime square. And L can also cancel with this square root L. So this will be equals to d prime R square root C over L. This we typically call it the characteristic impedance. Okay, now let's erase the blackboard. Okay, we have erased the blackboard. Now let's consider the impact of the controlling input, D cap. So we know that we have the controlling input related transfer function as GVDS. GVDS is called the control to output transfer function. So it is defined as the ratio between the output and the input, controlling input, given the condition that the other small signal input does not exist. So VG cap equals to 0. Therefore, we can modify the original small signal model since the input small signal source is considered to be 0. So here will be a short circuit. And this short circuit will also ignore the impact of this term. So this will also be removed. And furthermore, we can cross this primary side short circuit to the secondary side. So this can be also removed. So that is the resulting transfer function only considering the impact of control input D cap S. And next, we can, based on this circuit, we can further process it. So we have the L and the independent source here. So we can push them to the secondary side of the D prime to 1 transformer. So we push L and voltage source VG minus V D cap through transformer 2. Then we can modify those values, right? For the voltage source, since the coupling points are inverted, so we will have positive polarity downside. And this value will be VG minus V D cap divided by D prime. And the inductor across the transformer will be an equivalent inductor whose inductance is L over D prime squared. And we still have the current source here, ID cap C as well as R. So this is the output signal. So look at this resulting circuit. We can see that there are two types of sources. Both are determined by D cap. One is voltage source, one is current source. So it's kind of complicated. So our intuition tells us, can we use the superposition principle to analyze them one by one? So let's do it. So the step 1, we first only consider the voltage source. Therefore, we consider the current source is 0, which can be replaced by an open circuit. So here's voltage source. inductance L over D prime square, capacitance C. R, and output. So this is simple to analyze. We consider this as a impedance voltage divider network. So the ratio between output and input can be easily calculated, right? Output signal over controlling input in S domain will be equal to here, right? Here is the inverted source. So we should have a minus sign here. And then we consider the voltage derivation ratio. The numerator is the impedance of C parallel with R in S domain. Denominator is L in series with C parallel with R. So S O L over D prime square plus so that is the contribution from this voltage source. And next, we consider the impact of this current source. So step 2. We only consider current source. So here is the current source as ID cap. This will be 0, so which is open circuit. We no longer consider this branch. Oh no, so this so this is 0, which will be equivalent to a short circuit, right? So the L left terminal is directly connected to this terminal. So here is the inductance L over D prime square. And on the right-hand side, we still have this RC network. And this is output voltage. So for only considering the current source, this is also relatively simple. It's like a current source is the excitation signal, and its load is the parallel of L and C and R, right? So the transfer function Vs over d cap can be easily calculated, right, as this controlling signal for the current times the impedance of the parallel of those RLC network. So now we have analyzed them one by one. So step 3 is kind of combining those 3 parts. Combine the 2 parts. This is what the superposition principle tells us in circuit theory, right? So the complete control to output the transfer function will be equals to the contribution of those 2 parts. First part is minus, e.g. d prime R parallel with C, SL d prime square plus R parallel with C, plus the second part contributed by the current source, so which is I times R parallel with C parallel with L. So we are almost there, right? Then we can normalize this expression. Step 4. Normalize it. So we first rearrange the right-hand side of GVG. GVDS to be minus VG minus V over D prime times. We will see that this will be, the numerator will be 1 minus S times Li divided by D prime Vg minus V. And denominator will be 1 plus S L over D prime square R plus S square times LC over D prime square. And the normalized format will be similarly as what we did for GVG, right? So we can write the normalized format as GVG as equals to G0, GVD, right? GVD. GD0 times 1 minus S over omega z, which indicates there is a 0 in this transfer function. And the numerator is a quadratic pole response. So we have the standard format as 1 plus S divided by 1 over Q omega 0 plus S over omega 0 square. So this is the normalized format. We compare those two expressions and map them one by one. So we can see that this term is the DC gain, right? Which is GD0. So we can write the expression for GD0 equals to minus Vg minus V over D prime. Because this is a buck boost topology, right? So we know that for buck boost topology, its output voltage DC value equals to minus the voltage gain, which is D over D prime, input voltage. So we insert V2 here, right? So we can simplify the expression. So GD0 equals to minus Vg over D prime square. Or we can remove Vg and only keep V here. So this also be equals to V over D times D prime. And next, we look at the omega 0, right? Omega 0. Let me write here. If we compare those two expressions, we can easily tell the expression for omega 0, which is D prime over square root LC. That is the frequency of the quadratic pole, right? Quadratic pole. And next one is the Q, right? Q can be found by comparing this term, right? This term. So basically Q will be equals to D prime R times square root C over L. Last one will be the 0 here, omega z. By comparing those two, we can write the expression for omega z. Omega z equals to D prime Vg minus V divided by Li. And also, because for buck boost topology, from the DC model, we know that the dci equals to minus v over d times d prime times r. So we can insert this I to here to further simplify the expression. And the resulting value, by the way, we also replace Vg by V, right? So we can further simplify the expression for omega z. Will be equal to d prime square r over dl. Okay, so you can see that we have solved the DC bias and zero value and quadratic pole frequency and also the quality factor. Okay. So in this section, we have derived the two typical transfer functions for the buck-boost converter. We found that the GVD, right, control to output the transfer function, is essentially the right half plane 0, right, together with a pair of quadratic pole response. So based on those 0 and the poles, we can further analyze its body plot.